Okay, can you see my screen?
Yeah.
Yes.
Yes, okay, and you can hear me without any problem?
It's perfect.
Okay,
Thank you.
I will give a presentation with the focus on diagenesis, and the title is Effect of Diagenesis on Carbonate Reservoirs in Foreland Fault and Trust Belts. So really the focus on carbonate reservoirs and then different Foreland fault and trust belts that we have studied. François Roer already introduced several of these areas, and I will try to make a synthesis of the research that we carried out. I hope this will move now. Yeah. Okay. I will take my pointer. So the research was carried out in different Foreland fault and trust belts worldwide, and one of the reasons was that we intended to understand what is the diagenetic evolution in these complex areas, and to be able to separate the local versus the over-regional controlling processes, so that we could, to some extent, become predictive. And François already used a little bit the methodology. So there was seismic interpretation, there was trust pack modeling, there was thermal modeling. This was especially done by a splendid team from IFP. Also source rock characterization, and we carried out a lot of field work, especially focusing on reservoir analogs. So sequences in the outcrops which display the same sedimentary features as the reservoirs, as well as potentially the diagenetic overprint and structural deformation. So focusing on the one hand on the matrix porosity and its evolution, and then also on the fracture porosity, and trying to combine them to be able to understand the reservoir architecture. And this at the end should have allowed to carry out a kind of what we call the PVTXT modeling. So a modeling where we looked to the pressure, the volume of fluids, the temperature, the composition of the water, as well as the timing. And at that time, certainly this was rather challenging because, for example, the timing, we had a kind of relative timing, but nowadays we have new developments in carbonate diagenesis, which allows to really to have the absolute timing of a diagenetic event by, for example, the uranium-lead dating. Another feature is that we intended to have information on temperature. François already explained that this can be done by fluid inclusions, but it's not so easy, and there are many pitfalls, especially in carbonate minerals. But nowadays we have clumped isotopes. Clumped isotopes, that's indicated by this curious symbol here, the triangle with number 47. This is a new way of acquiring isotopic information, which can be translated directly towards the composition of the temperature. And once you have the temperature and also the oxygen isotopic signature of the calcite, yeah, then you can recalculate also the composition of the water. I will come back to this at the end of my presentation. Also nowadays, we are able to do the stable isotopes of individual fluid, fluid inclusions by crushing the samples. And this allows again to get more direct information that was not possible in former times. Also on the reservoir properties, we have now nuclear magnetic resonance, we have computerized tomography techniques, which allow much better to characterize the reservoirs, but I will come back on this at the end of my presentation. So why did we look to these Foreland fault and thrust belts. Okay, these are structurally quite complicated areas, and there was a need to support, I would say, the exploration, and where we tried to get an integration of the knowledge on the sedimentology, that's the framework, so to say, the diagenesis, and that's not only the petrography, but also the geochemistry, the fluid inclusion, microthermometry, and so on. Also the structural geology, and especially the mechanical stratigraphy. I will come back to this, what I mean by that, and to put all these features into a time framework, and which allows to see the evolution of the reservoirs. The focus was also to study the pore network and to link the 2D observations in thin sections towards three-dimensional features to understand the pore connectivity and how diagenesis is affecting this pore network system. And this, at the end, resulted in input data which could be used for modeling, and different scenarios were modeled to simulate the processes that are believed to have taken place and to some extent to become more and more predictive. So we studied different locations, and this should lead to that predictive model, which could help in exploration scenarios. This is one of these forward kinematic modeling that also Francois already showed. This is from Albania. So what is now quite important is that on the one hand, the colleagues from IFP were able to reconstruct, let us say, the evolution through time. We were looking to different potential outcrops and information from boreholes to look to the diagenesis. And in contrast to many studies that are carried out for diagenesis, which are much more, I would say, static models, a model about dolomitization, a model about autogenic quartz formation. What you can see already in this reconstruction is that what happens, for example, here at stage 2, at this location, will perhaps take place 10 million years later at stage 3 in this location. So it's a kind of caterpillar type of diagenesis. It's much more a dynamic way of looking to diagenesis, how this diagenesis is moving together with the different thrust fronts. The people in IFP were able in these kinematic models also to model the maturity of the source rocks and to see where it was over mature, where it was in the gas window and in the oil window. And the curious thing is that this type of modeling was highly developed over the last years, but there were no models really at that time looking to the water which is expulsed during tectonic deformation and the effect of this type of fluid flow on the diagenesis and on the reservoir properties. And this was then worked out by people from IFP to be able to put, apart from the thermal modeling or the maturity modeling, also the modeling of the fluid flow and the potential effect on the reservoirs. So field observations were quite crucial, and here we have already an example where we have matrix porosity in this dolomite and also some VUG porosity, cavern porosity. So we have to explain how this kind of matrix porosity developed, as well as how, for example, here in the Chogali Formation in Pakistan, where we can see that we have different cross-cutting relationships between different veins, and where we have then to try to understand which type of fluids were involved and which type of tectonic regime controlled the flux of fluid flow. Perhaps already this one, where we have the Chogali limestone, you can see that there is one vein with number 1, which is brown colored. So brown colored means automatically that it's iron rich, so that it's weathered, and the iron is a little bit oxidized. But one of the important things already by looking to this outcrop is from where is the iron coming? Normally, you do not expect that in the limestone itself there is much iron into the system. So the iron-rich veins indicate that the iron is coming from outside the limestone. So this is an exotic fluid. So this is an open diagenetic system, and open diagenetic systems are always of major interest because you can get creation or destruction of your reservoir. So the iron, the Foreland calcites or the Foreland dolomites, they are certainly important in our story. This is from the Dagny fields, a nice catoluminescence image. To the right, you can see that you have in the thin section different veins, but it's quite difficult to differentiate them. If you look to the left picture of catoluminescence, then you can see that you have a first generation, where you can even differentiate 2 subphases. Then vein number 2, cross-cutting the first one. Then number 3, which is brown colored, dull. And then number 4, which is very yellow. So people who know something about catoluminescence is the light that is created by bombarding a polished surface with electrons. And these electrons, they are interacting with the different minerals and they are creating some light. The color is proportional to the mineral. For example, calcite will often be a little bit orange or yellow. Dolomite will be more red. Fluorite will be blue, and so on. But it's also dependent on the trace elements which are incorporated into the veins. And one of the trace elements which is really lowering the intensity of luminescence is iron. So if there is iron in the mineral, then it will be more brown, more dull. And iron can only be incorporated in the calcite if the fluids were reducent. So when iron 2+ was present, and this is what you expect in a burial setting. In a burial setting at several kilometers depth, the fluids are reducing. And so if there is a little bit iron present, it will be iron 2+, and it will be then incorporated in the veins, and it will give a dark brown color, as you can see in vein 1, vein 2, and vein 3. Now, normally the limestone is formed under oxidizing conditions. So under oxidizing conditions, the iron will be present as iron 3+. Also manganese, if it's present, will be as an oxide. So normally the host rock will have no iron, no manganese into its lattice, and therefore it will give, it will be not luminescent, not much luminescent. But here we can see that the limestone is bright yellow, as, for example, part of the central vein, which is indicated here with number 4. So this is containing no iron, and its light, its yellow color is caused by the incorporation of manganese. A little bit manganese causes a bright luminescence. But that's quite curious that you have a vein in a burial setting which is not containing iron. So there is something happening which you can already hypothesize from the catoluminescence image. So in number 4, which is an apparently aggressive fluid, which is also recrystallizing the host rock, this aggressive fluid, despite its burial situation, does not contain iron. That's something which is very often the case when all the iron is going to be incorporated in pyrites. But if you like to form pyrites, then you need sulfur. So where is the sulfur coming from? It's coming from sulfate. And in this case, it's coming from sulfate reduction. So thermal sulfate reduction, there was a reaction between the hydrocarbons and the evaporites, causing H2S to form, which combined with the iron 2+ will form pyrites, and therefore no iron would go into the crystal, and the crystal would become, the calcite crystal will become bright yellow. So from the petrography, already you can propose a hypothesis that in this area potentially some thermal sulfate reduction affected the reservoir system. I will come back later on this. Very important in these Foreland fault and thrust belt systems are the development of stylites. Stylites, and we make a differentiation between bed parallel stylites, which relate to the evolution of the Foreland, of the burial cycle, as you can see in this picture a little bit, turbidites, which is oil stained, and where a stylite is developing bed parallel perpendicular to the sigma 1 of the burial cycle. However, with tectonic shortening, we will have compressional phenomena. The sigma 1 will be in a horizontal direction, and we will potentially start to develop layer parallel shortening stylites or tectonic stylites. And structural geologists, they tell us that this is happening prior to the thrust emplacement. So in the front zone of the thrust sheet that is moving by the tectonic forces, there you will have the tectonic stylites developing. You can see a nice example here. Also, again, these carbonate turbidites, which are oil stained, so the matrix has some porosity, but you can see also that the tectonic stylite has oil staining. So in this case, the tectonic stylite will become a quite important feeder system or a channel path along which some oil can migrate. The question is this open in a vertical direction, or is it more parallel to the bedding open? So there we will show you some pictures later from computerized tomography. Based on the cross-cutting relationships between the veins and also the cements which are in the matrix, as well as the stylites, we can work out a kind of paragenetic sequence of the different steps of phenomena that take place, with the burial stylites as one marker, and we can make an assumption at what depth they form, and then we can put the paragenesis into the burial evolution of the system. We can also assume at what stage for one area the tectonic stylites develop, and then we can separate the paragenetic sequence in different major episodes, so to say. But I mentioned already that when we did this study, there were still at the end many open questions, and there are new developments recently over the last 10 years, which really help us now and which would force us a little bit to redo our job. So for example, the paragenetic sequences reflect some relative timing of diagenetic events, eventually constrained by the timing of the stylite development based on some assumptions. When does burial stylites develop at 800 meters depth, for example, for that type of lithology, and so on. As I mentioned already, now we have the possibility to analyze calcite and dolomite by uranium-lead absolute dating. Also, the temperature of the vein formation deduced from fluid inclusions is sometimes questionable because we don't know if it's really the primary fluid inclusion or is it not reset by recrystallization. Okay, the salinity data, they can certainly help to some extent for inferring which is the fluid system. But now with clumped isotopes, we have the possibility to deduce the real temperature of formation. Paleo pressure, it's very, very difficult to deduce this before, but if you have the temperature of formation and the homogenization temperature of the fluid inclusions. Those people who know something about fluid inclusions, they know that the homogenization temperature is the minimum temperature of formation, and there should be a pressure correction. So if you compare the homogenization temperature without pressure correction with the clumped isotopes, which is the real temperature of formation, by deducting these two temperatures, you see the difference in temperature, and this difference is proportional to the pressure that happened into the system. If you have the temperature and you have analyzed the calcite crystal or the dolomite crystal, assuming equilibrium crystallization, you can also infer the composition of the water in SMO, and the oxygen isotopic composition of the water. But in fact, you can compare this then also with the isotopic composition of the fluid inclusions that can be analyzed. And then with regard to the porosity network and upscaling, we use computerized tomography as a 3D petrographical technique, and we did use especially matrix pore network information. And then by linking this to the mechanical stratigraphy, we can also link this to the fracture network that can be extracted from this mechanical stratigraphy. I hope you still can hear me, Mumtaz.
Okay.
Yes,
Yeah,
it's
okay.
okay.
Okay, perfect.
Yeah.
So we will now go to the rather important reservoir controlling events in these Foreland fault and thrust belts. And the first one is the preservation of the porosity, of the primary porosity. Okay, this is to some extent comparable to settings which are also not occurring in Foreland fault and thrust belts. It's mainly function of the sedimentary architecture, the presence of cements, and especially framework stabilizing cements, nucleation sites, and that's what I already mentioned, the framework stabilizing cements. These are cements, like you can see in the picture to the right, which glue all the grains together and which make them less vulnerable to compaction, be it burial compaction or tectonic compaction. So by a little bit cementation, you glue everything together, it forms a rigid framework, and compaction will have limited effect. Also, early dolomitization is of importance because dolomite is behaving differently, more rigidly, and then also the effects of recrystallization. So the recrystallization very often will cause an increase in crystal size. And if the porosity stays the same, then you know that if the crystal size increases, also the pore size will increase and the pore throats will be better connected. So this will have a positive effect on the permeability, and also the effect that already was shown by Francois of layer parallel shortening, which can create some anisotropy in your system. I come back immediately to this. Here we have an example of framework stabilizing cements. These are these turbidites, and they are oil stains, as you can see. So the black color is oil stains. The red arrows indicate defining upward sequences. And in this case, whenever we had turbidites which were more than 30 centimeters in thickness, we had some units of the turbidite in the lower part which contained matrix porosity, and this matrix porosity is linked, in fact, to framework stabilizing cements. So I will show now a thin section of the lower part of the turbidite, the lower part, and then of the part which is stained by oil. If you look to the lower part, there are many fossil fragments, and there is a lot of cementation. So it's over cemented, and so above the rudist fragments you have a cement forming, which is closing nearly all the pores. And the pores that are present, they are not very well connected. However, if you have the oil-stained lithologies, then you see that there is some micrite present. So this is a kind of packstone, also with these fossils, these relicts of the Rudists, but you have cementation, but not so dramatic as in the left example, due to the fact that the micrite was stopping, in fact, the growth of the cement. So in this case, it was especially the presence of micrite which made that some of the porosity was preserved, primary porosity, and also that later some secondary porosity could develop. Here, this is some computerized tomography images where you can see the case where there is no oil staining and you have individual. So we made the rock transparent, the limestone transparent, and we only show the voxels, the areas where we have porosity. And you can see there is porosity, but it's not very well connected. The other one clearly shows that there is much more porosity and that the pores are indeed connected. Some 10 years ago, we were able to do CT scanning with a resolution of 10 by 10 by 10 micron. Nowadays, the new instruments allow resolutions below 1 micron. So this is also something which is developing very fast. Here we have the dolomite that Francois already showed, where you can see that there are stylolites developing between the crystals. The layering is here in the vertical orientation, so the sigma 1 is horizontal, so to say, and these are layer parallel shortening recrystallization phenomena, which make this type of reservoir anisotropic. So in one direction, you will have better connectivity between the pores than in the other direction, parallel to the layering, so to say. And what is also visible in the picture to the right is that within the crystals, we have some cleavage planes that develop, and these cleavage planes, they develop also perpendicular, parallel to the layering, or in function of the sigma 1 orientation, this recrystallization took place. As I mentioned, recrystallization is often taking place. Here, an example of a dolomite, a cathodoluminescence image of a dolomite, red colored, typical for a dolomite. You can see that the dolomites originally were most likely zoned, but by the picture itself, you can see that it's a kind of obliterated color plate, with some places only red, other places only brown, other places still zoned. If you see this under cathodoluminescence, you know that there has been some recrystallization going on. And very often, the recrystallization will also be manifested by the formation of bigger crystals. Bigger crystals means that if the porosity stays the same, that you create bigger pores and better connectivity, and this will certainly also affect your permeability. The pathways for fluids will become better. So this is something to take into account, that in several of the Foreland fault and thrust belts, dolomites can recrystallize, can have crystal enlargement, which is good for the reservoir, but very often there is a kind of anisotropy due to the layer parallel shortening. Another quite important event in Foreland fault and thrust belts is what happens in the forebulge. In the forebulge, these sediments potentially can be affected by karstification, and so by infiltration of meteoric water. And apart from the karst phenomena, which can happen at the shallowing upward cycles, where a sedimentary origin can be linked to the karst, you have the potential to create in the forebulge some karstification. And remember, by the thrust sheets which are moving towards the foreland, you have this forebulge karstification at different episodes, different times in each of these sheets. And you can also have a post-foreland thrust belt development of karstification. If, for example, there is some uplift of certain thrust sheets, and if a second stage of thrusting happens in some areas. What is also very important is that once you have a karst system in these carbonates, these karst systems, they act as a kind of anisotropy system, and very often you will see that fluid expulsion will occur along these paleokarst systems, and that there is some special diagenetic overprint and potentially the formation of additional secondary porosity. Here are some examples of these secondary pores, okay, partly cemented, but related to additional karst formation in these foreland fault and thrust belts. With the isotopes of these cements that you could see, we could confirm that there was a kind of period of karstification with soil-derived CO2, which caused some of the dissolution and the cementation. That's what is called in the isotope world the inverted G trends. So normally the marine carbonates will have a value typical for the time period that they formed, and which is close to the zero value, which is the rectangle here. And very often you will see that you will have cements which are more negative than the marine water in relation to meteoric water, but some of these cements, they will also have negative carbon signatures because soil-derived organic CO2 is taking part in the entire system. Third important reservoir controlling event is the development of stylites. I mentioned already the bed parallel stylites and the layer parallel shortening stylites. You can see them again into these drill cores. Remember that many boreholes are drilled in a vertical way, so the chance that you encounter these tectonic stylites is not so likely, but they are very important because you can see if I have my anticlinal structure and I'm bending the layers, then these tectonic stylites or layer parallel shortening stylites, they will open, and this will potentially allow circulation of fluids or circulation of oil in these systems. The question is a little bit, is this connectivity that you can see by the oil staining, is this in a vertical sense or is it more in a lateral sense? Again, here we can use computerized tomography, and you can see in the different sections that if I reconstruct this in 3 dimensions and I make the rock again transparent, that it's not, let's say, along the stylites, but much more within the rock itself, that the connectivity of the stylites is present. So showing the strength of this super technique of computerized tomography to visualize what is really the connectivity of the different pores. Also, the stylites, they act, once they have been formed, as heterogeneities, and in some cases fluid flow is really controlled by these stylites, like here in this case of an iron dolomite, which is enhancing the reservoir properties of this limestone. And then obviously a very important reservoir controlling factor is the fracturing or the fractures. And based on the stylites, we can recognize the veins which are pre-bed parallel stylites, pre-compactional stylites, which are post-pre-bed parallel stylites, but before the layer parallel shortening stylites, or if the veins cut the tectonic stylites, the layer parallel shortening stylites, then they clearly are later. And this helps to differentiate different generations, which then can be characterized by catoluminescence, by isotopes, by its fluid inclusion, composition, and so on. And this allows to tell you whether the veins are host rock buffered. So if the material in the vein is coming from the host rock, and that means that it's a kind of closed system, or whether this is an open system and where you have exotic fluids coming in. I can tell you already that once you are in the stage of what happens after the layer parallel shortening stylites, you very often are in an open diagenetic system. So a very dynamic system. So here the fractures of a certain area that have been mapped and where the blue indicate pre-folding set of fractures and the black ones are the syn-folding fracture systems. The cross-cutting relationships are very important. So there where they cross each other, the veins, there is the place where we drill. And that's the reason why we not hammer, because then it would break at this contact zone. No, we will drill at the place where we have the cross-cutting relationship, be it with the bed parallel stylites or with the tectonic stylites, as you can see here. Catoluminescence of these veins, which is cut in this case by a stylite. If you look to the color, to some extent, the color is quite similar to the color of the host rock. In this case, this would point much more to the bed parallel, to the host rock buffering, to a closed system. Also very important that you can see here are the cleavage twins. The cleavage twins, they clearly show that the vein has suffered some tectonic stresses. So this is certainly a vein which formed before the layer parallel shortening stylites developed. And this allows them to work out a kind of story which is pre to syn bed parallel stylites with different orientations, post bed parallel stylites but before the tectonic stylites, and then what is happening post tectonic stylites. What is also of importance is that you should be aware that where big faults occur, that the diagenetic history in the footwall or in the hanging wall can be different. This is an illustration of such a system that we have studied, where we looked to the footwall, hanging wall indicated by the symbol H, and then the F for the footwall. Many of the veins were developed before tectonic compression. If we look to the isotopic composition of the footwall system, then we have a system which for carbon is clearly controlled by the host rock, which is indicated here. The host rock would be this rectangle. There is a little bit lower values, but overall it stays around one specific delta 13C value. The lowering in oxygen isotopes is most likely related to meteoric water or increase in temperature. If we go for the hanging wall, normally the original marine signature would be this rectangle, but you can see that there is clearly lower carbon and lower oxygen values in the isotopes, indicating that the systems are different. Also here you can see the hanging wall indicated by H3 has higher temperatures, homogenization temperatures than the footwall system, and also the melting temperatures are different, giving different salinities, as you can see here for the hanging wall, below 6 weight % sodium chloride, and if we look for the footwall, it's clearly highly saline. And so we came up with a model where the fold was sealing, forming a permeability barrier, and where in the footwall we had the infiltration of migration of warm saline formation waters, which did not affect the hanging wall. Fractures are very important, but especially fractures that testify of overpressure are intriguing, like the hydraulic fracturing, as you can see here, or the crack and seal fracturing. The crack and seal, that means the pressure is building up, and at a certain moment you fracture your rock. By fracturing, you have the release of the overpressured fluid, which is going to seal the fracture, but at that moment you build up again the pressure and it's increasing. Again, fracturing happens, sealing happens by cementation, and so you can see different episodes of this release of overpressured fluids. You can also see that some of the crystals have been broken off. If you see this, then you can be sure that overpressure has affected your system, and this could have also its importance. Again, if you do the cathodoluminescence and the isotope studies, you can have an idea whether the fluids which were overpressured were testifying of a closed diagenetic system or an open diagenetic system. And if it's a closed diagenetic system, you do not expect much aggressive fluids to be involved because the system is buffered. However, if it's open, then you can have a lot of very special things. That's something curious. Sorry. That's a pity. Here normally there should be a picture of a dolomite that has been fractured, and quite important is to consider that if you have host rock dolomites, they fracture much more in a cataclastic way. They have an other rheology and rock mechanical behavior than limestones, so that's something you have to take into account. I don't understand why it's missing. And some special cements that can occur. So especially here in the middle part, you can see that you have a kind of zoned crystals. Also here, some crystals which have some curious centers, also under cathodoluminescence. You see that they're a little bit exotic. And in this case, by looking to the isotopes, we could prove that bacteria were involved, and bacteria which were interacting with some hydrocarbons. So here we have the release of some hydrocarbons due to the breaching of the seal, and the oil which is migrating came into contact with bacteria which caused these curious exotic crystals. These type of textures are very typical for interaction with bacteria. And also the isotopes testify of the presence of these hydrocarbons. Here, a very special case, which has a lot of importance, of transgressive conglomerates on top of an anticline. So we have an anticline which was deformed during fault and thrust belt formation, and it has been eroded. And the erosion products still occur, are unlapping the anticline. And if we look to the conglomerates, we can see the different components of the limestone which is making up the anticline. We can see, for example, here a very fine grained limestone from a turbidite, where we have a bed parallel stylolite, and it's cut by a vein. So that's happened before the conglomerate was formed. However, if we look to the conglomerate in a slab, a polished slab, we can see that between the fragments we have tectonic stylites and also cut by a vein. So that means that after the first anticline was formed and eroded and the unlap of the conglomerates, we had again a tectonic deformation in the system, which is affecting this lithology. So we had sedimentation with bed parallel stylites. Then we had deformation with different veins that formed and tectonic stylites. It became eroded. It became affected by meteoric infiltration, karstification. the conglomerate was deposited, unlapping the system, but then we have a new burial cycle which deformed the conglomerates and also the tectonic stylites inside, and there was also additional veining. So that means that in this case, we have to assume that we have two episodes of burial, and that could lead to two stages of oil charging, depending on the depth of the burial in each of these cycles. So despite the fact that these unlapping conglomerates very likely do not form a reservoir, they tell something very important for exploration, that potentially you have two charging periods in this system. And then, yeah, sometimes you have very exotic processes that can affect your reservoir system. Here we had a refill limestone, which was dolomitized, but the refill components, sorry, the refill components were not dolomitized because sorry, because they were formed out of a rigid calcite, and later on the calcite was selectively dissolved, creating this vuggy porosity. We have some of these fossils from metaporoids, because they were already quite lithified. They have not been dolomitized, and they were selectively affected by some dissolution of the calcites, and then some of the cavities were filled by dolomites, calcite, quartz, and also sulfur. And if you have sulfur in the system, you have to be careful, because that could indicate that you have thermal sulfate reduction. And this is also again visible in the isotopic record of the cements which are filling these cavities, where we can see that we have very negative delta carbon 13 values, which indicate the interaction with hydrocarbons, or part of the CO2 is derived from hydrocarbons which have been oxidized by the dissolved sulfates. Also, if we look to the strontium isotopes, they are very exotic. So the fluids are coming from outside. Also in the cements, we could indicate the presence of lithium. Lithium is normally not present in any carbonate. So this means that there is an external source of this lithium, and the material most likely came from interaction with siliciclastics. Another very important process that creates porosity is what we call topography-driven or squeegee fluid flow in Foreland fault and thrust belts. So we have meteoric water which is infiltrating in the elevated areas. It's heating up when it's going down into the system, and it's squeezed out of the Foreland fault and thrust belts. But by squeezing out of the system, it very often will cool. And Francois already indicated that cooling of formation waters is a system which can create some porosity. Here, a dolomite, where some fossil fragments were originally present. These fossil fragments were not dolomitized, only the micritic matrix of this waxstone was dolomitized. And later, this cooling of formation waters, they started to dissolve the calcite selectively. So this is a very important process, and I will explain it more in detail by this graph, where in the vertical axis, the calcium 2+ in equilibrium with calcite is given versus the temperature. And there are different lines that you can see, which show the equilibrium lines for a certain partial CO2 pressure. Let us take the partial CO2 pressure of 50 bars. If we have a fluid which is in equilibrium with calcite at 120 degrees, the composition of that water will plot on this line in this point. If I'm able to bring this water to a temperature of 80 degrees, so cooling it, I enter into the domain where I'm undersaturated with respect to calcite, and so I can dissolve this amount of calcium from calcites to reach again equilibrium. This is what we call cooling of formation waters. It depends on obviously on the water composition and on the number of parameters like pH and so on, but it's a quite important process. So if you have water at high temperature in equilibrium with calcite and you can bring it to a lower temperature, you will have potentially, or you have the potential to create some secondary porosity. So that's the story of this bioclastic WAC to mudstone. You have the fossils in blue, dark or blue, and then the other color is indicating the matrix. We had selective dolomitization. The fossils were not so much affected because they were quite crystalline. And later on, by this cooling of formation waters, we have the selective calcite dissolution in the burial real. You even can think that if you have a trust sheet at 5 kilometers depth and you bring it to 2 kilometers depth, even you don't need real fluid flow. The fluid which is present will cool and will potentially create some secondary porosity. And then obviously reactivation of the systems, the fractures as well as the layer parallel shortening, some pictures that Francois already showed. These reactivations are very important, and especially if you have steep anticlines. If you have a steep anticline, then you will see that in the area where the bending is highest, you will have the opening of the tectonic stylites and the different fractures, while in the flat limb here of the anticline, the opening will be less clear. So that explains sometimes the difference in production in some of these oversteeped anticline systems. I will come now to these new developments. One of these new developments is clumped isotopes. So in contrast to the classical oxygen or carbon isotopes, where you analyze one element with a certain isotopic composition versus another, the same element but with another isotopic composition, delta 18 versus delta 16, for example, O18 versus O16. In clumped isotopes, you analyze a more complex configuration of elements. That's what people call isotopologues. Isotopologues is, for example, calcium CO2. If we have carbon and oxygen, then the carbon can have different isotopic compositions and the oxygen also. And we speak about clumped isotopes when the natural abundance of molecules containing two heavy isotopes occur. So in the CO2, there should be two of the components consisting of the heaviest isotope. I give the example, CO2 with one carbon-13 and one oxygen-18. So this is the clumped isotope. And if we analyze the calcites, we will analyze this clumped isotope 47, which will help us to understand the preferential built-in of this heavy isotope into the chemical bond. And if the temperature is very high, it will be a value which is defined as 0. But if it's forming at lower temperatures, we will see that the heavy isotopes by preference will go into the crystal, and therefore, based on these clumped isotopes, we can deduce the temperature. So here we have a reaction of different CO2s mixing, and if we create this clumped isotope, and this preferentially will be incorporated into the crystal, then we can infer the temperature, because this composition indicated here with this triangle with 47 as suffix, you can see that the correlation is only dependent from the temperature. So this is a real major development in the field of isotope characterization of carbonates. Also fluid inclusions. Nowadays we have devices which allow us to crush this sample and then to analyze the water composition of the fluid inclusions. And this will allow us then to deduce what is the water composition of the fluids involved in the formation of this calcite. Here an example from Albania, where we had the early pre-folding veins and then the synfolding veins. And you can see the synfolding veins, they plot in this plot of the water composition, oxygen composition with respect to hydrogen. We have the global meteoric water line. So we can see that the synfolding veins are more meteoric, while the pre-folding, they show a mixing of an end member which is meteoric and something which is going towards an evaporite end member. And this helps us to reconstruct then the types of water involved and the mixing of these types of waters. So if you have a Foreland fault and thrust belt, then in the first stage, so we will have the topography-driven ascent of meteoric water, which with circulation along open mode fractures parallel and perpendicular to the trend of the foreland. That's what happens in block 1 here, or in this area, block 2. And then the late stage fractures, they develop parallel to the direction of tectonic transport or perpendicular to the tectonic stylites. That's what happened in the stage of the late stage deformation. I mentioned already that one of the critical parameters that was very difficult to deduce in former times was the Paleo pressure. But now we have the possibility to calculate the Paleo pressure based on the clumped isotope temperature compared to the temperature of the homogenization. I mentioned already the homogenization temperature of fluid inclusions is considered to be the minimum temperature of formation of the crystal, and there should be a pressure correction carried out by plotting now the TH values versus the temperature deduced from clumped isotopes. You can see that for the different components that we studied, I will show them immediately, they plot below the 1-to-1 line. So that means that the clumped isotopes give higher temperature than the homogenization temperature. And if you accept that this is related to the compensation that you have to calculate for the pressure correction, you can calculate the pressure based on these graphs. And you can see in this case that the zebra dolomites testify of much higher pressures than, for example, the hydraulic breccias that has been studied in this study. So this is a way, to some extent, to calculate the paleo pressures. And finally, the super technique of uranium lead dating by laser ablation ICP-MS. You see here a vein, and in this vein, by laser ablation, we have analyzed the different isotopic compositions of uranium and lead. And you can see that for the different sampling points, the red one, the blue one, and the yellow one, they plot along in this graph along a certain line, and the inclination of this line is proportional to the age of the vein. And you can see that this vein formed about 110, 113 million years ago. However, I have to be honest, this uranium dating technique is not every time successful. Sometimes there is too low uranium lead variability, or there has been some recrystallization occurring, or there is not enough initial lead present, or too high initial lead present. So from my experience, it's working in 50% of the cases, but if it works, it gives crucial information, obviously. And then the super technique of computerized tomography. What I like to show in this picture is, in fact, the tomography of a core but where we not only looked to the porosity, the distribution of the pores, but where we also manipulated the attenuation of the X-rays to infer where the anhydrite was present, where the dolomite was present, and so on. In fact, if you look to the theory of computerized tomography, you can either work out information on porosity, or you can also deduce mineralogy. And that means that you can do petrography in 3 dimensions, so to say. What also is interesting is that if you have these type of pore distributions, you can plot inside these voxels, where the pores are, you can plot kind of approximate ellipsoid with a longest axis, an intermediate axis perpendicular to it, and a smallest axis. This allows you to work out a kind of classification where you plot the intermediate versus the longest axis versus the smallest over the intermediate axis. And this domain can be split up in different types of pores. The equant ones, which are rather homogeneous, I would say, while the other ones, the bladed or the roller type, they clearly display a certain anisotropy. So apart from getting an idea about the type of pores and sometimes also the pore connectivity, you can also get information on the anisotropy of your pore system. And based on these reconstructions, you can calculate the permeability by lattice-Boltzmann simulations. Experience shows that these simulations, they are quite good in accordance to the real permeability that has been measured in these samples. Another super technique is what I call LiDAR, where we use laser light, or photogrammetry, which is more convenient nowadays because it's you can do it with your mobile phone. You take pictures from the wall of a quarry, overlapping pictures, and by reconstructing these pictures, you can work out a kind of 3-dimensional model of the quarry. In this case, you can map out the different planes that are present, the orientation of the different planes, and you can do a statistical analysis. And also quite important is that you can reach areas which are inaccessible to take measurements, and by this you will increase the amount of data that you can collect. You take as the outcrop at home, in fact, which is always quite interesting. You can work also the mechanical stratigraphy. What is mechanical stratigraphy? In former times, people were saying that the fractures develop independent from the lithology. But in reality, we can see that in tin-bedded lithologies, we have another type of fracture behavior than in thick-bedded lithologies. And the thick-bedded lithologies are more often in limestones corresponding to grainstones, while the tin-bedded are more often corresponding to waxstones or mudstones. And in function of which type of lithology, you will see that you will have an other density of fractures, also with other orientations, and potentially also the opening. So in thick-bedded units, you more often have less fractures, but they are more open than in thin-bedded lithologies, where you have much more mudstone. You have also much more stylites which can develop. Therefore, these lithologies can act as a seal. You will have more fractures, but they are much thinner and very often completely cemented. So this is also a domain which is very interesting in Foreland fault and thrust belts. And this brings me to the conclusion a little bit. So based on the entire reconstruction of the paragenesis and the help of isotopes, fluid inclusions, clumped isotopes, and so on, you can reconstruct the sedimentation history, the first forebulge karstification, then the development of bed parallel stylites, and where the thrust sheets form the layer parallel shortening stylites, the overtrusting, and the different episodes of veining, as well as potential additional karstification. So In Foreland fault and thrust belts, the reservoirs are dual reservoir systems. We have a caterpillar type of diagenesis, so the front is moving with the thrusting. It's more dynamic. We, on a regular basis, have systems which are overpressured. We have also focalized fluid flow along fractures, but we can also have more diffuse flow. However, in the first case, focalized fluid flow, and we will have a lecture this afternoon on such a system, we can have, for example, preferential dolomitization along certain lithologies. There, the mechanical stratigraphy could explain some of the distributions, so this is quite important. Also, recognizing the open or closed system diagenesis is of importance, because the closed system is not so reactive than the open system, because the open system, there the fluids are often not in equilibrium with your host rock. In dolomite strata, in Foreland fault and thrust belts, we often have the recrystallization. Remember that we have also some exotic processes. I didn't go too much in detail, but we can have also mixing water systems, which can create dolomite, which can create aggressive fluids. Cooling of formation waters is a very important one, thermal sulfate reduction and so on. And in Foreland fault and thrust belts, you are forced to link the diagenesis to the structural geological evolution. And if you are successful, to some extent, some of these processes can be predicted, can be modeled, and can help in the exploration. Thank you for your attention.
Thank you very much, Rudy. Very nice, comprehensive on the of processes involved in the fold and thrust belt. Might have some echo in the system. So if you have some questions from the participants, we can go ahead with few questions.
Yeah, go ahead.
Yeah, Dr. Mona Lisa is there, so if you can ask a question, please, Dr. Mona. Your mic is mute. Please unmute the mic. Dr. Mona.
Thank you, Dr. Mumtaz. First of all, I must congratulate you for organizing such an informative session for all of us. Although my field is not carbonate sedimentology, but there are some slides which are linked with tectonic stylites. I have a question from Professor Rudy Swennen, and I must say that his presentation for a person like me, who is not an expert in carbonate, but I have some information related to tectonics and tectonic regimes, especially. In one of your slides, Professor, you have said very well described tectonic stylites.
Yes.
Here, you must know, you must better know that there are various types of tectonics regimes, like translational and transfrational and compressional and tensional, etc. My question is that, is there any kind of differences in tectonic stylites on the basis of these various tectonic regimes? If yes, then what effects can they produce? Especially in the last slide, in the conclusion slide, you have mentioned in the last point that there is a linkage between linkage of diagenesis to structural geology as well. So I would like to find out, is there any relationship or is there any differences on the basis of different tectonic regimes as well?
That's a good question because, by my knowledge, this has not been studied yet. And in reality, you have to think, or the reality is that it's not so easy to understand the development of tectonic stylites, because if we go back to the compactional stylites, there it's quite easy because you can accept that during sedimentation, you had the accumulation of some clay and organic material during a period of low sedimentation. So you had also some micrites with a high reaction surface, and that's the place where the bed parallel stylite, the compactional stylite, will develop. However, if you go to the tectonic stylites, then such a preferential layer is not present. So many people assume that originally there were some joints along which these tectonic stylites develop. But in reality, or by my knowledge, nobody really has gone in full detail. And then linking also the type of tectonic stylites to the tectonic regime. This would be quite exciting, yes.
Okay. So do you think that there is a possibility that anyone can work on this new aspect of tectonic stylites?
I think this would be very promising. And if there would be a kind of link to tectonic regimes, this would be highly important, especially for the anisotropy that is created by these tectonic stylites. As I showed you in computerized tomography, the porosity along this stylite, tectonic stylite, was along one direction, but not in three dimensions, so to say. So there is something which is controlling the development and the opening of the system and causing their potential contribution as pore networks along which some hydrocarbons could migrate, yes.
Thank you very much, Professor.
Thank you, Dr. Mona Lisa. To introduce Dr. Mona, Professor Rudy, she's my colleague. She is expert in atomic seismology. That's why you have a question related to the different tectonic regimes with the.
Yeah, but I think it's
yeah.
It would be quite exciting to do this, but then you have to define areas where these tectonic regimes, where there is no overprinting of one regime by another phenomenon. That will be quite tough, I think.
Yeah.
Yeah.
Thank you.
Yeah. I must thank my Professor Rudy for such a remarkable presentation as well, and I'm quite sure that this new aspect which I mentioned, it will help. I'm a seismologist, like Dr. Mata said, but I think this new aspect can be addressed further.
Yeah. Thank you.
Thank you.
Now we go to the OGDCL office where they have some question. Maybe some of you may have raised hand in from the OGDCL. So yeah, please go ahead. Yes, you can hear from OGDCL. We have a hand raised over there. So if there is any question. Okay, so we don't have a question from there. So Professor Rudy, a nice presentation. I have one question regarding the techniques. What you have described to get the fluid inclusion phases out of the inclusions and to study them for various purposes, like for isotope studies, for other geochemical analysis. What is the basic way to get these inclusions out of it? So I'm much interested in methodology of it. Thank you.
Yeah, it's a kind of crusher device where you crush the crystal So you liberate the fluid inclusions. That water you heat, and you bring it to a device where there is a cooling place, so that all the water will form some ice crystals, and that can then be coupled, that device, to a mass spectrometer, which is then, or this device is then heated suddenly to 1000 degrees. So all the water will evaporate again and will be steered towards the mass spectrometer, where then the delta O18 SMO value can be measured. Now, this is a device which is not commercially available, so there are a number of labs which have developed this. I can bring you in contact with some of these labs. There is now a big debate going on, because in principle you can do the reverse now. You can analyze the crystal, so you have the delta O18 PDB. You have measured the fluid inclusion in SMO. Then, in principle, you can calculate the temperature of formation, and you can compare it with the temperature deduced from clumped isotopes. And then it seems that in many cases, or in several cases, that these temperatures are not fitting together, and that the temperature deduced from the measurement of the fluid inclusion is too low. And this has been linked to some additional interactions that occur between the fluid inclusion and the crystal, and that there is a kind of exchange during the cooling history of the veins under consideration. If you are interested, I can send you additional information on this.
Yeah, but sure. Thank you. We'll be discussing it later. Thank you, Professor Rudy. Any other question from the participants? If there is any question, then please ask. Okay, so there is no further question. So thank you once again, Professor Rudy, for giving us time, and a very nice presentation you had, which elaborate from start of the field observations, and then you went all the way to the modern techniques being used in the field of carbonate sedimentology, relating it with the diagenesis and other processes being involved. So thank you so much, Professor Rudy.
Yeah. Okay, no problem.
Thank you. Okay, so it was the second talk of the morning session regarding the third presentation of this morning about the presentation of Lakhdar Benchila, as we had communicated that we have some last-minute changes in the program because of the some engagements of Dr. Lakhdar Benchila. So we are canceling it, but Dr. Francois, are you going to give some talk, or it has already been done?
No, I am done with my talks.
Okay. So then we will have a break for about until 4 o'clock local time. It means 12 o'clock European time, and then we will start the second session.
Okay, thank you.
Okay.
Thank you, Rudy.
Mohammed. Hello,
yeah.
Mohammed.
Yeah.
Just to be sure, because I should be the first for the second part. So you mean 12 Italy, Belgium, and France hour?
Yeah,
so
exactly.
Approximately in 1 hour 50 minutes. That's okay?
1 hour 50 minutes.
Because here now it's 10:08.
Yeah.
So we will
So
go
we'll
back
start
in
at midday.
Okay.
Midday
Okay.
there. Okay.
Perfect.
Okay. Yep.
Thank you.
Okay.
Alexander.
Thank you.
Just to be sure.
Thank you. See you.
Okay.
Bye.
See you soon.
See you soon. Bye.
Bye.